Catherine est très connue pour être une géochimiste isotopique, spécialiste de la géochimie du manteau, de la formation de la croûte. Elle travaille aussi sur la géochimie appliquée à l'érosion de la croûte continentale. Elle est fellow de la GU, la Geochemical Society. L'année dernière, tu as donné la conférence d'Ali à la GU, qui est quelque chose d'assez prestigieux. Il y avait beaucoup plus de monde encore dans la salle, qui était énorme. Je me rappelle. Voilà. Donc, merci beaucoup. On t'écoute.
C'est vrai qu'on voit pas très. Vous m'entendez? Oui. On voit pas très bien l'écran d'ici. C'est vrai que c'est un petit peu compliqué. Oui, donc je vais vous parler d'un point. Maybe I should do it in English. Yes, okay, I'll do it in English. So I'm going to talk about a geochemist's point of view of how the Earth's crust and the mantle interact. So this is a work that I've been doing over several years, and I put pictures of the main people who contributed to what I'm going to present today. So there is several PhD students, Marion Carpentier up there, Chazal Abanier here, and Marion Garçon here. A fourth PhD student here, Hélène Delavaux, who now works for Thermo Fisher. And some of you might know from here, who moved from Paris to Grenoble, Eric Lévin, who has been contributing a lot to all sorts of calculations. Mantle and crust. So how do we look at it when we are geochemists? What I'm going to talk about today is the differentiation of the Earth that created the mantle and the crust, and what happened between the beginning of Earth's history, the Hadean, when there was no crust, as kind of shown on this picture, which is a bit of an artist's point of view, but it's quite nice. All the way to the present situation shown here, with ocean, continents, and the mantle below. From a geochemist's point of view, the differentiation is very simple. It's boxes. We have the core that was formed at the very beginning of the Earth, and then there was a starting material that we call the primitive mantle or bulk silicate Earth. This part of the Earth differentiated to create the crust and the mantle, the residual mantle. About 40% of the Earth's surface today is continental crust. The rest is oceanic crust. But so the question I'm going to look at today is when and how the continental crust formed, how much of this crust is sent back into the mantle, try to quantify that, and what impact the recycling of that crust has on the mantle in general. So to do this, I'm going to take you through a journey that starts from in the mantle to create the crust and goes back into the mantle through the cycle of erosions, sedimentation, and subduction zones. So I'm going to start with the continental crust and the present situation. Today, in the Earth, the crust is the very thin layer at the top. It represents 40% of the surface of the planet, and because it doesn't look like that when you look at a map, but in fact 30% of the continental crust is underwater and is not really seen, so the surface is a bit larger than one imagines. It's a thin layer, on average about 40 kilometers, and in terms of mass, that's what's important, it's only 0.52% of the mass of the Earth. It is in fact very little. So why is it important if it's so little? It is important for us in geochemistry. This is the first geochemistry diagram. There are going to be a couple more. This is a present situation when you look at the trace elements in the continental crust. This is an estimate of the enrichment in various trace elements listed here with their symbols, enrichment relative to the primitive mantle concentration. So what we see here is that the estimate of the total continental crust done by Roberta Rodnick, who gave a talk, I think it was about a month ago, shows that there is an enrichment factor of about 100 for the most incompatible elements. I think my pointer is going to stop working there. And the enrichment is smaller when you get to the other end of the list, but is still significant. It's like 3 times, roughly. So there is a lot of trace elements in the continental crust. It's very rich in trace elements, particularly the most incompatible elements shown here. So if I make the budget in a different way, and I look at the proportion of the element that is in the crust relative to what is in the bulk silicate earth, which is basically the earth minus the core, so it's crust plus mantle, you see that the proportion can be very high, up to 50%. And but for a lot of elements here, the least incompatible elements, it's only an arrangement factor of 2 or 3. Some of them are very high, cesium. Here is the very high one as well, which is lead. So it is a lot, it's a high proportion, so this is why it's important for geochemical budgets, when we want to make the budget of what happened in the Earth over time. So what is the effect of the formation of that crust on the mantle? Knowing that the Earth started with a primitive mantle value, so here that would correspond to a line of 1 everywhere. At the beginning of the Earth, we had a line of 1. And today, we have that much of the trace elements that are sequestrated into the continental crust. So the impact on the mantle can be quantified. If we say that the entire mantle is a residue of the formation of continental crust, in other words, it's well mixed and it's the balance in terms of budget, then it's what the mantle should be like is shown with these blue dots. So it's a slight depletion in the most incompatible elements. In contrast, if only the upper mantle were to be depleted as a consequence of formation of the continental crust and the rest of the mantle would still be primitive, then we would have the green dots. And you see that it doesn't change very much things at this end of the diagram, but it has a drastic effect on some, and for a lot of elements, all of those here, plus lead here, it's simply impossible. It's not enough left. There's nothing left. So it's impossible. So the reality is definitely somewhere in between the two. I think from a trace element point of view, it's impossible to have only the upper mantle that's been depleted. And we have some evidence otherwise than the mantle is more depleted than if it was the entire mantle. So it's somewhere in between. So how large is a depleted mantle? This is an approach that's been done by my colleague Bill White, who I was working with in Mainz a long time ago. And he made this estimate, which is basically by looking at the concentration of one element, neodymium, where we have an isotopic constraint, we can make a mass balance to calculate the mass of the depleted mantle using the isotopic composition. So what he showed, it's a bit of a complex figure, but what he shows is that the estimate for the concentration in the continental crust relative to bulk solid earth is this line with a relatively large error. And if we take this estimate and then we take the neodymium isotopic composition of the primitive mantle here, as neodymium is 0, which is what we generally agree on, it gives us about 30% of the mantle that is depleted, that compensates for the formation of continental crust. if the primitive mantle was not chondritic, as had been suggested in the recent years, but is still highly discussed and probably was a bad interpretation. But if it's much higher, shown like by this line, then you see that in some cases it's simply impossible because you need to have more than 100% of the mantle that's depleted. So the take-home message here is that probably we should stick to these values, and it's probably about a third of the mantle, which is more than the upper mantle. So when did the crust form? There was a talk by Bruno Duim not long ago who talked about that, but it's just a figure that he gave me that shows as we go through time of the age of the Earth, beginning of Earth history here to present day value here, and estimates done by all sorts of people. Initials correspond to papers. All sorts of people of the estimate of the volume of the continental crust at a given time. So we have two extreme type of models. We have the model, the Armstrong model here, where basically everything was created within the first few 100 million years, and then the volume of continental crust didn't change, remain what we know now. And the other extreme is this model here, where most of the crust was created extremely recently, less than 1 billion years ago. So there is a big range. And so there is all sorts of argument to discuss, whether such a model is better or that model is better. But it's not, we still don't know. There's still a lot of discussion going on about that. So how can we move forward with that? We can try to make a budget of the composition of the present-day continental crust and see how it can provide answers for such questions. So how do we calculate? What we do in geochemistry is we calculate model ages. Model ages, and I put this little sketch figure to show how it's done. Here the time, is the other way around. The beginning of Earth history here, present day today. And it shows how we use isotopic composition here, 143 neodymium over 144, evolution through time. The chondritic reservoir, the primitive mantle, is shown with this green line, and an evolution of the depleted mantle is shown with the blue line here. So what we can do is measure all sorts of crustal sample to try to define the present value and the range, and make an average and use the parent-daughter ratio, samarium and neodymium, to estimate an age. That's a model age. And the model age here is shown as the model age relative to depleted mantle. These are not real age, but it's just an average. It provides an average. So that's what I've done in a paper that I published a few years ago to estimate the average composition of the upper continental crust. So what we did is we worked on loose samples because they are good samples to make an average very simply in one sample. You have a very large surface that has been eroded and lands in the same sample. So we analyzed a lot of loose samples. You don't see them because they are behind the star, and there's about 50 points all stuck there. So what it shows that basically the loose provide a very uniform average value. The only exception are the Argentinian loess here because of the overwhelming quantity of recent volcanism in the crust that's been eroded. And so the important point here as well is to show that it's a good way to make an average because you can compare the data that are all stacked there with the range of individual crustal areas that define a very big range here in hafnium and in neodymium isotopes. So we think that such average is probably representative of the upper continental crust, and then we can provide an average value for neodymium and an average value for hafnium. And we could compare it in this paper with what had been published. Actually, it's very little published for neodymium. There is some estimates shown here, and hafnium there was absolutely nothing. So we can go one step further and we can calculate the model age using the neodymium data that I just showed before. And so we plot the parent-daughter ratio here versus the isotopic composition here. All the data points are stuck behind the big star here, and that gives us an estimate for both the neodymium and the samarium-neodymium ratio. Having these two parameters, we can calculate an age, and we get a model age that is not very old, as a matter of fact, is 1.8 billion years. Okay. So how does this compare to the curves? This is a line. That's a value, the 1.82 billion years that I mentioned. So we see that the upper crust would tend to suggest that crust formation occurred maybe more recently than all these models suggest. But it's only upper continental crust. It's not the whole crust, and the whole crust might be different. So if I go back to my figure, which I showed the model ages, we can try to estimate the model age of the total continental crust instead of having just the upper continental crust. And here I use the same sketch. I plot here the neodymium isotopic composition that we estimated for the upper crust, used the samarium-neodymium ratio that we calculate as well, and we get an age, 1.82, okay? Then we don't have anything for lower and middle continental crust. There is no estimate. So what I did is I took the estimate of the samarium-neodymium ratio suggested by Roberta Rodnick, and I just used different ages, starting the oldest possible at 4.2 and change the age. And see then by changing the age, you get different slopes, and the purple star moves up. And then by using the mass proportion of lower plus middle crust and upper crust, we can estimate the isotopic composition of the total crust depending on the age of the lower plus middle crust. And then we can calculate a model age for the total crust. So I've done that in a theoretical way here. It's a plot that looks a little strange because it's a TDM versus TDM. But what it shows is that here is the model age that we have for the upper continental crust. And here the model ages that I vary theoretically for the lower plus middle crust. So when the lower plus middle crust is very old, here 4.2, then the total crust shown here by the gray line is very old, and it gives an age of 3. If the lower and middle crust are more, on average, younger, then the total crust on average is also younger. The take-home message I want to show here is that basically we don't have isotopic constraint for the lower and middle crust. The data don't exist, and we don't. So I think that's something that needs to be done, but it's not very simple because there is no loess that mechanically sample upper and lower crust. So it's not easy. The other important thing I think to remember is that for having a model age for the total crust that is 3 billion years, the age that has been suggested by, maybe I go back, there. This is the new models suggested that by Bruno Duim, by Chris Hawksworth, by actually quite a lot of people, saying that half of the crust was created 3 billion years ago. Then the model age should be 3 billion years ago, because the model age is the average. So if you have a model age of 3 billion, it means that half of the crust was created before and half of the crust was created after. And that requires, when I look at my figure here, it requires that the lower plus middle crust model age is 4.2. And I think it's going to be difficult to demonstrate that the lower and the middle crust are that old. We can, have serious doubts about that. So anything younger will make the total crust model age much younger. Okay, so that's the open question for that part, the differentiation between mantle and crust. Now I'm going to move to the sedimentary side of the cycle. And what I want to look here, show here is the effect of the sedimentary process to modify the composition of the material that is eroded from the continental crust. We know the composition of the upper continental crust, but then when the material is eroded and transported and deposited, the composition changes. The soluble elements are transported in the rivers, so they go in the water. The insoluble elements are transported in mineral phases, and they end up in sediments. New phases are also created by biology and autogeny. So the end result is that what is in the sediment does not have the same composition as what was eroded. And that has an impact for the general cycle. Here is a picture that I stole from Jérôme's chapter in the Treatise of Geochemistry, where he shows a whole list of elements, very, very big list, and they quantified the chemical mobility during erosion and transport. When the numbers are small, it's a log scale. When the number is small, it means the element doesn't go in the water phase. And when it's very high, like at this end, it shows that it's very soluble and goes in the water phase. Most elements are not very soluble. You see that they're below 1. And what is important from my point of view, my perspective, is that the elements that are parent-daughter in the radiogenic systems the ratio of the two elements can be modified. You see, for example, that uranium can be quite highly mobile, but it's not the case of lead. So if we lose a lot of uranium, then it will have effect on the lead isotopic composition because of the decay constant. Similarly, rubidium is a lot less mobile than strontium, so it has an effect on the parent-daughter ratio. But what I want to concentrate on is the sediments more than the water. So here are a bit of a complex figure, but I think that's important because it addresses the issue of the thorium-uranium ratio. Thorium-uranium is a very important ratio for long-term evolution of the Earth because it determines the lead isotopic composition of the material, the mantle and the continental crust. It's a ratio that's kind of very uniform in magmatic rocks, and it's 3.8 for the primitive mantle, bulk silicate earth, the continental crust, and the depleted mantle. A new estimate has been published, I think it was 2 weeks ago. With a lot of data and a very good compilation. So it's very uniform and it's 3.8. When you look at sediments, the situation is very different. So here I highlight a compilation done by my previous student Marion Carpentier, where she plotted the uranium concentration in the sediment versus the thorium concentration in the sediment, and she compiled data from all sorts of arcs. Here are arcs in front of Vancouver Island in Canada. There is a Lucian, there is all these arcs in that area. And here are some sediments that come from the erosion of, in front of arcs sediments that originate from places where there are old cratons. So here, for example, it's the erosion of the Brazilian craton and so on. Here is there is the erosion of Australia and so on. So anyway, the observation that we made was that the blue dots where young crust is eroded are significantly different from the yellow dots, which is where old crust has been eroded. We could even plot the ratio of the two elements as a function of the model age of the area that have been eroded, and we see that the blue dots here, young, have a low thorium-uranium ratio when the older terrains provide some much higher thorium-uranium ratio. It can be plotted in a different way here, and we see that on average the young terrains provide a low thorium-uranium ratio, actually even a bit lower than the continental crust value. But what is important is that when the crust has been exposed at the surface for a very long time, the ratio is very high. It reaches 7, which means that there is a preferential remove of uranium by the rivers, and it has a very important impact on the lead isotopes on the long term. The sedimentary material is going to have a very specific evolution in lead isotopes. Now looking at a different system, I'm going to move to the Ganges basins in India and Bangladesh, and here's a work being done by my student Marion Garçon, who worked on river sediments, shown by the stars here, from the Himalaya all the way to the delta here. There's a lot of sediments there, so in terms of quantity, it's important for the budget of sediments in the world. And it's a long river, and the sources are quite diverse because there is the Himalaya here, but there's also the Deccan Trap and the Indian Shield. So there is a lot of diversity in the sources. So what did we see there? What happened during sediment transport along this very big river? I plotted here is the altitude where the sediment were sampled along the river. So here is the Himalaya, going up, and the samples were collected mainly in the plain. So you see, it's low altitude, all the way to the ocean. What we see is that whichever samples are measured, they always have the same neodymium isotopic composition. It doesn't change when you go down the river. In contrast, going down the river, the hafnium isotopic composition changes, and the variability increases more and more as you go down. So there is a sorting due to the mineral, with the heavy minerals being stuck at in the bed loads, in the heavy fraction of the sediment, and the lighter minerals being transported at the top of the river, which means that they go further away and they have a higher chance to go into the ocean than the bed load samples. So there's this decoupling that occurs during the transport. And so do we see that when we go in isotopic space here? She plotted all the data for all the samples along the river. And what we can quantify is what we call big delta hafnium isotopes, which is I really have troubles to see the figure from here to show how it works. But anyway, what happens is that when the coarse-grained sediments have no decoupling in terms of hafnium, they are on the line here, the terrestrial array, and the finer the fraction, the higher the decoupling is. And at the top here, we have the clay samples, the fine-grained samples. And this is because most of the hafnium is contained into the zircon, and the zircon are stuck there on the terrestrial array. But the decoupling occurs in the fine-grained sediments. So when we get to the ocean, the situation the same situation occurs. And the difference between the fine-grained and the coarse-grained increases. And this is the case of two sites in the Cascadian arc located here. One is closer than the other to the continent. And when we measure the composition of these samples along these two sites, you see, but I think you don't really see very well because it's too little, but the light blue have show a spread that is smaller than the fine grain here. The delta hafnium shows that the higher the fractionation is, the coarse grain are here and the fine grain are here. I can't see the figure And another example here, in front of the Lesser Antilles arc, we measured samples from two sites, one close to the continent, the other one further away from the continent, and we see the same thing. The orange dots show that there is little decoupling in the sediments, the coarse-grained sediment from the site close to the continent, and a much larger decoupling when you go further away from the continent. So what does it do to the ocean, to the sediments that will basically potentially enter the subduction zones? That's what it does in terms of neodymium hafnium isotopes. It shows that depending on the mineralogy, the composition is different. And it is systematic. The coarse-grained sediments lie along the mantle array, close to. All the clays lie above, and the most extreme case is the iron manganese crust and nodules that capture the composition of the seawater mainly and have very decoupled hafnium isotopic composition. So that's basically the only place on Earth where there is, at a large scale, a decoupling of the two isotopic systems, because all terrestrial rocks fall on that line, whether they come from the mantle or the continental crust. And, nicely enough, we see that the impact of these sediments is seen when you look at what happened in the island arcs. In island arcs, we see that all the data lie here, and they define an array shown by the orange line here, which I call the island arc array. And this array is significantly different from the mantle array, and it is due to the recycling of these sediments that are decoupled with a lot of clays and probably very little coarse-grained sediment. So we see that there is a bias that is introduced in the arc due to the processes that created the sediments. So what else happened in subduction zones? I'm going to go through that a little a bit quickly. I guess most of you know that in arcs there are two enrichment processes. There's a fluid transferred with a ratio of highly mobile to less mobile element, and there is some sediment melting here, quantified by this ratio. This is at the word scale, the range that is observed in arcs. There is two big enrichment processes that are different. In some arcs, there are both. And I wanted to show this figure because there is a Lesser Antilles arc here where both processes occur. And so it shows that the transfer from the mantle wedge to the arc can be done in two different ways, and it's not only fluid transfer, and it's not always fluid transfer. Sometimes the sediment melts. And just to show you that on the map, if I take the lesser Antilles arc here and plot the data as a function of latitude, I take the index of sediment melting, and we see that in the north there is no change, no sediment melting, and a clear signal in the south of the arc. If I take now my fluid mobility criteria, then we see there is a big range in the north, quite a bit range here, in fact, a lot less in the south. So it's consistent. The fluid transfer in the north, sediment melting in the south of the arc. So the way the element move is it varies depending on where you are on the arc. But what I think is very interesting is that when the fluid transfers elements, and in particularly strontium, we can trace the origin of the fluid and the strontium in the fluid by looking at the strontium isotopes. And what we see is that for the high strontium-thorium ratio here, all these rocks, the isotopic value is very low, so the strontium does not come from the sediment. The value is too low. It must come from the subducted basalt. It cannot come from the sediment. We could also make a budget, more generally, of how much of each element is sent back into the mantle and doesn't go into the arc. And we see here estimates I've done with my colleague Jeff Ryan. And we see that for some element, everything that enters the subduction zone as sediment is basically sent back into the mantle. These are all the immobile elements, hafnium, thorium, the heavy rares. 90% of the element is sent back in the mantle. It's not the case for these elements, and for example, lead, it's only half of the lead that's sent back into the mantle. And there is a range in between. So that creates significant fractionation of isotopic parent-daughter ratio again. And that will affect the long-term composition of the mantle. Another estimate that was published by Bill White and his former student, where they managed to make an estimate, which is very difficult to do, of what is sent in the mantle using the composition of the basalt and the sediment that enters subduction zones. They can calculate how much is sent back in the mantle for each of these arcs in terms of trace element pattern. You see that a lot of barium is sent back, and for some elements it's enriched, and others are not enriched. It's just like the starting material. But a lot is sent back. So how does it, I'm just going to finish now, going back to the deep mantle and the effect of all of the recycling of all this material into the mantle. The canonical pictures from White and Hoffman paper in '82, and where they showed that the crust was recycled. Maybe it's stored somewhere. It might be the source of ocean island basalt. But some is certainly mixed back in the general mantle. So I'm going to focus only on the ocean island basalt compilation done here by Al Hoffman, where there are various types, and I will not discuss all of that. I just want to talk about the end members that are enriched, where we think we could see some signs of recycled continental material, and these are the orange and the yellow dot here, EM2 type and EM1 type that you can see in the various figure. So EM2, I think EM2, we have a very clear case that in this basalt there is definitely some continental contribution. Definitely. They have high strontium isotopes, low neodymium isotopes. They have intermediate lead. but more importantly, they have low niobium-uranium ratio. This is one of the two canonical ratios of Hoffman, which are very strong constraints, as a matter of fact, very, very strong constraints. So it's very difficult to change this ratio, and the only way to change it is to introduce material coming from the continental crust. Similarly, the other canonical ratio, thorium-lead, can be demonstrated to be low when the strontium is high in the Society Island, which is part of some of those points here. So these two ratios show very clearly that there is an influence of continental material introduced into the mantle through sediments that is involved in the source of these lavas. EM1 is less clear. It's probably old, but we didn't know how old it was. And then there has been this new data that came from a completely independent isotopic system, the MIF sulfur anomalies, shown here with the capital 33 sulfur. And the point here is that to have a value that is different from 0, here is a figure from James Farquhar, to have a value that is different to 0, you need to have a material that is older than 2.4 billion years. And in some of this present-day lava, we found some anomalies shown here by the black dots by doing in situ analysis of sulfur grains in minerals. So that's an argument to say that the material that's present here was at the surface more than 2.45 billion years ago. So it's recycled. So it's probably of sedimentary origin. But there is a problem. Because here are the red dots, which is the individual analysis that we've done. And so we measure the whole rock, and the whole rock has no anomaly. That's a work that has been done by Émilie Thomaseau here with Pierre Cartigny's group. And so that raises an important question, which is how can we reconcile the two? And that's not very easy, I think. It's not very easy. It definitely requires more work. More data, because Cabral et al. Published these green dots here, demonstrating there was some negative anomaly as well in a high mu type of island. And so I measured some high mu island here, the green dots, no anomaly, 0 anomaly. And I measured a couple of samples from the EM2 type, the yellow dot here, no anomaly. So right now, we are in a situation where there is no anomaly to be seen when we measure bulk samples, when there's been anomalies seen on in situ analysis of small grains. So, to summarize, I'm sorry, I have some summary and some questions, or some future work, let's put it this way. So first of all, the crust and the mantle have been interacting for a long time. I think I will convince you of that. The surface processes modify the composition of the material removed from the continental crust. So what enters the ocean basin does not have the composition of the continental crust, and we can quantify that. This material is then sent back into the mantle through subduction, but the subduction factory also changes the composition of the recycled material, because some elements go in the arc more easily than others, and we can quantify that. Finally, the recycled material can be identified in the source of soil mantle magmas, and it certainly modifies the composition of the mantle as a whole. The question that I think is still important and needs to be answered are the following. What is the average age of total continental crust? We need to do that, and I'm not sure how we can do it, because I don't see any clever way of sampling lower and middle crust and be able to analyze it. The second big question, which I didn't talk about at all today, is the effect of processes other than subduction. It's been suggested by several people, in particularly Peter Kellerman, that processes such as delamination or relamination could modify the budget between mantle and crust as well, and subduction zones might not be so important. So I think these are effects that should be quantified too, and it's a big job. And finally, the question is there any anomalies in present-day volcanism? We have contradictory information, and we need to solve that. Thank you.
So questions.
Alors, qui veut être les premiers ou la première?
I start to start the question.
In English, sorry.
I start.
Okay.
So when you show how you calculate the modelage for the extraction of the crust, the continental crust at the beginning, for the upper crust, you calculate it relative to the evolution of the depleted mantle.
Yeah.
But it seems strange to me not to consider that part of it is made by the reworking of the differentiation of the lower crust itself. And so if you would calculate relative to that, you would not find the same edge, specifically when you show that, of course, the lower crust is older than the upper crust. So
we don't know. We simply don't know.
Yeah, but in your diagram, it could be. So there is a possibility.
I know it's theoretically.
Yeah.
It's theoretically. It can be younger. It can be older. It could also be, in fact. I think
for me, there is a possibility. You could calculate what should be the amount of reworking of the lower crust, so that the upper crust and the lower crust have, in average, the same bulk edge, something like that. No, when you look to if you go back to your diagrams before this one, yes.
Yeah.
So the source of the upper crust is not obligatorily the depleted mantle.
No, it's not. So it's a lot of recycling. It's a lot of cannibalism by itself.
Yeah, so it
comes from the upper crust, and it also comes from lower and middle crust as well. But that's a composition today. The average composition today. It's a point there.
Yeah.
And what we don't know is this line and this point.
Yeah.
So that's. But this is not a single event that created from a unique reservoir. It's a lot of reworked material as well. But on average, it's 1.8, which means that half of the upper crust is older, half of the upper crust is younger.
Yeah.
Yeah.
Okay.
Yes, Catherine, so from the present day, we know that the composition of sediments can be eroded from the continents, can be very different depending on the setting.
Yeah.
A mountain is not giving the same types of sediment at lowland, blah, blah, blah. So do you think it could be something possible to trace this kind of weathering regimes back in the past of the Earth, or is it something which is too low to be seen? You see, in the mantle. Or
no, I think it's possible to do that on all sediments, definitely. To see, just quantify whether it was freshly eroded crust or old material that's been reworked several times. I think it's very feasible on all sediments. Yes. Definitely. Yeah.
Interesting.
Questions? Then maybe I have one. You mentioned that the fluids were actually coming from MORB, from the subducted basalts, and not from the sediments. Yet we know that sediments are somewhat full of water. So is this wrong, or where are the fluids going? Fluids that were initially in the sediments?
I think that the fluids that were initially in the sediment might have gone, have left the subducted plate maybe before getting to the place where the arc is formed. Okay. In the fore-arc, I mean closer to the subduction place. place. Yeah, I think that's probably what it is. I mean, there is the mud volcano. I think you might not have heard about, like Barbados. And this is, I think it's probably coming from the sediment. It's, yeah, maybe there's some data. I mean, strontium on, such mud volcano would just give the answer immediately.
Yes,
Hi, Catherine, I saw you in your slide that you showed that for sediment, when the erosion, the source region, they have different rocks. They can have different thorium uranium ratio.
Yeah.
And what's the explanation for that? Is it source effect?
No, I think the explanation is that it's this thing, the difference between that and that. I think the explanation most probably comes from the fact that the old crust has been exposed at the surface for a much longer time than the young crust, and therefore the uranium has been removed over a long period of time by water.
Okay, because what I'm also thinking is because we know that uranium can have different mobility when you have different oxidation state.
Yeah.
And is it possible that it can help chase the weathering process in the past or not? If you change this ratio, you will change the lead isotope composition in different ways. Probably it can work.
Yes, but I think if you want to look at old samples, is that what you're trying to suggest? Looking at old sediments? Sorry, I somehow I'm confused about your question now. I'm just realizing.
No, I mean, I'm just thinking about why, the rocks have different age, like the older rocks, they can have...
because it's just older, it's cratons. It's areas that are eroded that are old. It's like when you erode the Himalaya. The Himalaya is a young mountain, but all the terrain in the Himalaya is very old. They are all cratons that have been brought up by the collision. It's old rocks to start with. Okay? It's a craton. The Amazon basin, the Amazon basin is is eroding a lot of old cratons, Archean stuff. Australia is the same, and it's making sediments that go in the ocean, and it's an erosion of an old craton. And this is when sediments erode old cratons like that, then you have the high ratio.
Okay, so it is just because of the leaching of the uranium with time?
I think so, yeah. Okay. I think that's what happens. Yeah, it's not the co-signature of the rock by itself when it was created.
Thank you.
Yeah.
I have a question about the thorium-uranium ratio you are showing here. What I've seen in the past, that we saw that the depleted mantle was at 2.5 for the thorium-uranium ratio. Why it's now different in this Wilberforce study? What's new? I didn't follow that for.
No, because it depends on whether you look from the lead point of view or the instantaneous ratio. And if you want to look at the reservoir, you have to start from the lead point of view and calculate kappa values. And kappa values tells you it's 3.8. Always. It's never been 2.5 with kappa value. No, it's a lot more than that. I didn't look at all the paper in detail because I just saw it a few days ago, but I can look and tell you later. I haven't read it, but I know it's a major compilation. That's what I saw.
We could have said that if the thorium-uranium ratio was different in the depleted mantle, you can expect that the young crust is formed from a depleted mantle, and that the old crust is formed from a primitive mantle. So
but it's
different thorium-uranium ratio.
Yeah, but it's not the case.
The thorium-uranium ratio is now the same.
Yeah, it's the same. Yeah. So it's not the origin. Yeah, that's right.
Okay.
Yeah, I have a question about all mantle convection or a more complicated convection. And you admit now that you can have all mantle convection, but it's not so easy because sometimes some slabs are trapped in the transition zones. And I was wondering, maybe it's a stupid question, can we discriminate sediments coming from, for example, recycled sediments coming from the transition zone or coming from the D double prime layer or deep in the mantle?
I don't think so.
No.
No, I don't think we can make a difference. We don't, we geochemists don't know where the things are. You know, we don't. It's complementary. Yeah.
Just coming back to the question of the strontium isotope source, the more one in arcs.
Yeah.
Would you suggest is fluid transfer through by hydrated fluids or a melting of slab?
I think it's strontium that comes from the. Where is it? It's here. That's the Antilles. I think it's strontium coming from the subducted basalt. Yeah. And for some unknown reason, no strontium comes out of the sediment that is overlying the crust. So I don't know what's, it's an interesting question, I think, for experimental petrology to find an explanation for that. Yeah. But I think it might be because most of the fluid from the sediment is gone before reaching that area, that depth. Yeah.
In some cases, strontium is correlated to chlorine.
The
Have you been?
Or the concentrations?
Yeah, concentration.
Yeah.
For the isotopes, I don't know. There are data or not? Strontium chlorine isotopes. No.
I don't know. No, but if it goes, it's consistent with that. That's good. Yeah.
To go to your last slide, so what are the possibilities to explain the fact that the bulk lavas do not have the same sulfur isotope composition?
I think I prefer if Pierre answered the question. I mean, to me, because it's not really my specialty, but I would say that I see two alternatives. Either there is an analytical problem somewhere, or when we do in situ measurements, we select a type of grains that is specific inside minerals. So we choose them, and maybe the total budget of the sulfur coming from other grains can be dominated by sulfur grains that don't have an anomaly and that are not located inside minerals. I don't know. That's the only two things I can think of. Maybe Pierre has more ideas. He certainly does.
Well, the study of Cabral was not very good. They did not really pay attention to mass, to the fraction. Yeah. How do you call it? Instrumental mass fractionation.
It's the green dots there.
That's really the one showing the lowest anomaly. The other data have been produced by Emilie Tomasso at CRPG Nancy, and we looked at the data, and they are very, very stable through time. And it's very hard to argue for a problem of measurement. My opinion, or my question would be whether when the sulfide form, whether there could be an isotope fractionation when the sulfur diffuses in the melt. And if the sulfide gets trapped in an olivine, and the time scale is too short, then you can preserve some isotope diffusion, isotope related effect that will not occur in the melt. Maybe, maybe not. What we need to check is actually getting like a bulk measurement on a single sulfide, and then we can really compare basically the same type of samples that we cannot do so far. Manuel, you didn't understand? Yes. Nobody can calculate that. I talked to Ian Borg, who does this kind of calculation. He said that we could probably approach it from a theoretical point of view, but we basically need empirical data to understand whether diffusion of sulfur in a melt would be mass dependent or not. So we don't know. Well, when I look, so it's Richter's work, etc. When they put the beta values to predict the fractionation, it's most of the time empirical. So I don't know if we can predict mass-independent fractionation during diffusion so far.
Maybe one thing to do would be to take a rock sample and systematically analyze all the sulfur, whether they are in grains or not, and see what happens in situ. That might help as well. I don't know.
Very close to doing this. In terms of mass balance, all the sulfur is on the sulfate. Are you missing a reservoir somewhere?
I don't know. I don't think so. Yeah.
For combination with basalts, when the melt evolves and crystallizes, you lose about, say, 30% of the sulfur as sulfide. So the melt will keep 70% of the sulfur. So you have a positive reservoir.
Yeah. I think that Emily measured the sulfate on the bulk. She did the sulfate and independently, and I think it's one of these red dots. It's there. I think she did that. Yeah.
Okay, so I think we can continue to discuss at la médiathèque. Okay.
Okay, let's thank the speaker once again.
Thank you.